Alright, so I'm taking a look at section 4.4 now. 4.4, the decomposition theorems. It's kind of interesting to think about. Suppose I just give you a matrix A, and I say, is it possible for us to break A apart into a product of matrices? And of course the answer is yes. There's lots of different ways. Let's just take a look at a few. From linear algebra, in fact, we know that there's something called the LU factorization, where U is an orthonormal matrix and L is a lower triangular matrix. There's also a way of decomposing a matrix A as Q times R, and we talked just briefly about that in our attempt to find a random orthonormal matrix. So that's another way you can decompose a matrix A. Is there any other way of doing that? Sure. In fact, there's an infinite number of ways. If you just write A is equal to B times C, right, there's an infinite number of choices of B and C that will work here for a decomposition. So you might be saying, well, why are some decompositions better than others? Well, some decompositions, like the QR and some of the ones that we're going to talk about today, actually give you a lot of precise information about the four fundamental subspaces that are associated with the matrix, and that's a really important thing, and we'll get into that in more detail. But yeah, there is a problem that's kind of interesting to think about. Well, maybe I'll give it to you later. It's something called the blind signal separation. And so the idea behind blind signal separation is you've got, I guess I'm going to talk about it now. Suppose you're standing in a room, right? So lots of people are standing here. And the idea here is that there's a conversation going on, and so that conversation is some kind of mixture of signals, right? Each person has their own signal that they're outputting, and so when you're standing in the room, you're getting different combinations of those signals. And so in particular, suppose you have two microphones, or n number of microphones, if you will, and each one is picking up a different different combination of the voices. So suppose you have n voices with n microphones, then what your signal, the signal that you're going to get is going to be a matrix that has time running down here and n signals here. And so the idea here is that you want to try to unmix this using a matrix so that, whoops, the new matrix that you get, the output matrix, is going to be each person's voice, unmixed voices. And this is a mixing matrix. And this is the sound we recorded sound. Okay, so this is called the blind signal separation problem, and it's because you just have these signals and you don't know how they've been mixed. But of course we're assuming that there's a linear mixing going on, and in fact that's violated somewhat in microphones, but we're kind of glossing over that for now. We're just using linear mixtures. And as it turns out, there's a really nice way of unmixing the voices. We might try that later on. It's also called independent component analysis. Independent component analysis, or ICA. So that's kind of a fun problem, and really the basis for this problem is, given a matrix A, you're trying to figure out different ways of decomposing the matrix into different products, right? And so this product has certain nice properties that we would have to define. Okay, so somehow we'd want to get unmixed vocals here. That's kind of fun. Okay, we're not going to do that much fun stuff right now. Well, we may later. It's not really hard to do, but I don't want to get off too far of a tangent. So before we do that, I'm going to talk about a different decomposition, and that is the decomposition that we use for eigenvectors and eigenvalues. And you're familiar with that. A is n by n. And so, we've already gone through the eigenvector eigenvalue definitions, but the idea here is that there is a matrix. Let's call it P. This is not a projection. Not a projection. Not necessarily a projection. It could possibly be one. And a diagonal matrix D such that A is equal to P times D times P inverse, right? Do you recognize that? If you can do this, if such a decomposition exists, A is said to be diagonalizable. Diagonalizable. Is there an E in that? Diagonalizable. Good. And of course, the way the diagonalization works is that the matrix D has your eigenvalues. So what are you going to need for that? You're going to need a full set of eigenvalues, right? You don't want to, that's counting multiplicity. Of course, that's easy to get, but you don't want complex numbers here. And then P is the set of eigenvectors. And so what do you need in order to make sure you can construct that? You need n linearly independent eigenvectors, and that can be hard to do, hard to guarantee. And so if I just give you an arbitrary n by n matrix, there is no guarantee that A is diagonalizable. Okay? That's a problem. And so there is a certain class of matrix that's going to cure that problem. And the cure of that is the matrix that is called symmetric. So symmetric matrices. Darn it. Oh no. My eraser is going bad. I think my computer is getting heated up. Symmetric matrix. A is symmetric. Do you remember what it is? If A equals A transpose. Good. I'm going to pause that for just a sec and I'll write down the main theorem. Okay, here we go. The main theorem is called the spectral theorem, and it is on page 49 of the notes. Okay, and so let A be n by n and symmetric. Then 1. A has n real eigenvalues. Excellent. Number 2. For each distinct lambda, the algebraic and the geometric multiplicities are equal. What does that mean? Remember that the algebraic multiplicity is how many times lambda is repeated as a root to the characteristic equation, And the geometric multiplicity is the dimension of the eigenspace corresponding to that lambda. When we're working with like a 2 by 2 matrix, usually there's just one, the geometric multiplicities, but for larger matrices we can have an eigenspace associated to each lambda. Good. And so the eigenspaces, and again that's the space spanned by the eigenvectors. The eigenspaces the eigenspaces are mutually orthogonal so if they're distinct eigenvalues, right, then the eigenvectors are going to be orthogonal to each other. E lambdas are orthogonal. But suppose that I have like lambda equals 2, 2, 2 is repeated 3 times. Then I've got the dimension of the eigenspace is 3, and so the eigenvectors, you could choose any of the combination of eigenvectors, right, in that space, linearly independent, to represent your basis. So that in that sense they may not be orthogonal. However, you can choose an orthogonal set to represent your basis for that space. So that's what we mean by saying the eigenspaces are all mutually orthogonal, even if you have the same eigenvalue. We're going to see that later. So if you're not sure what that means, don't worry about it right now. 4. A is orthogonally diagonalizable. Meaning that we can rewrite A as V times D times V transpose, where V is the set of eigenvectors, D is the set of eigenvalues, that's the matrix. It's a diagonal matrix with the eigenvalues along the diagonal. And V is, the columns of V are orthogonal, so we might as well make them orthonormal. So V is orthonormal. Good. And so therefore V transpose is equal to V inverse. Good. So again, I've run over time today to describe this more. I think what I'll do is I'll stop here and we'll save this discussion for next time. See you then.